Another example I want to look at here is related to hyperbolic functions. And so you should have seen this in pre-calculus, but it happens so fast that many students forget. And so we've got a whole family of what are called hyperbolic trig functions. I'll define hyperbolic cosine. And its definition is e to the x plus e to the negative x all over 2. And its counterpart, the hyperbolic sine, is equal to e to the x minus e to the negative x. So it's e to the x minus e to the negative x all over 2. So if I want to know what is the differential of hyperbolic cosine, so the differential of hyperbolic cosine is equal to the differential of e to the x plus e to the negative x, all divided by 2. And this differential, so this is a constant, 1/2. I'm really multiplying by 1/2, so it can factor out. And my differential will distribute over addition. So this is equal to, and I'm just going to put it at the bottom. So this is equal to the differential of e to the x plus the differential of e to the negative x divided by 2. And this is equal to, well, the differential of e to the x is just e to the x dx. And the differential of this, so this is going to be plus, so think of this as our u. So this is plus e to the negative x, the differential of negative x, all divided by 2, which is, well, the differential of negative x is just negative differential of x. So this is e to the x dx minus e to the minus x dx over 2. And bringing that dx out, this is the whole thing, e to the x minus e to the negative x over 2 dx. And this is what we define to be hyperbolic sine. This is simply the hyperbolic sine dx. So, similar to our trig functions, the hyperbolic cosine functions have the same feature, that the derivative of cosine h, or hyperbolic cosine, is hyperbolic sine. Similarly, let's, just for good practice, let's look at our derivative of the hyperbolic sine. So the differential of the hyperbolic sine is the differential of e to the x minus e to the minus x divided by 2, which is equal to the differential of e to the x minus the differential of e to the minus x divided by 2. And differential of e to the x is e to the x. And we just calculated this before. This is negative e to the x, which makes that a plus. So this is, but maybe I'll go slow just so if you missed it last time. So this is differential x minus e to the negative x, and it's d minus x. And again, because that, I don't have an x in the top, I have negative x. That's my u in my differential form. So it's du right there. Of course, I'll divide it by 2. And those negatives cancel. And so I get that this is e to the x dx plus e to the negative x dx all divided by 2. Factoring that out, e to the x plus e to the minus x all divided by 2 dx. And that is our hyperbolic cosine. It's what it's defined as. So this is the hyperbolic cosine dx. Again, these functions show up, especially in differential equations, but they're really just exponential functions in disguise. One last example in which I want to use transcendental functions to find the equation of the tangent line. So let's find the equation of the tangent line to y equals x minus log base 2 of x, where x, say, equals 8. So to find the equation of a tangent line, the two things we need a point on the line and we need a slope. So we know the x value, so then the y value, so when x equals 2, y is equal, or sorry, x equals 8, y is equal to 8 minus log base 2 of 8. Now this is a value you should be able to calculate, because what is this saying? Log base 2 of 8, what is it equal to? So over here, if I say what is log base 2 of 8 equals some number. Well, what number? Well, that means that 2 raised to the n power has got to equal 8. Right? So 8 equals 2 to the n. Well, what number would give me 8? Well, 2 to the third power, right? 2 times 2 times 2 is 8. So this tells me that n is 3. Because that's the only number that I raised 2 to. Too many 2's. When I raise 2 to the third power, I get 8. So telling me that log base 2 of 8 is 3. So this is equal to 8 minus 3, which is 5. Right, so our point, we're going to be at the point 8, 5. So what is our slope? Well, our slope will be the change in y with respect to x at the point x equals 8. Right? That's the slope of our curve, so that's the slope of our tangent line. So that means we need to compute the derivative of x minus log base 2. So let's do that. We know that the differential of x minus log base 2 of x, differential rule distributes across subtraction, so this is dx minus differential of log base 2 of x. And scrolling up to our rules, the differential of our logarithms, so this is log base 2, is 1 over natural log of our base times our input du. So differential of log base 2, this whole thing is just dx, that doesn't change, minus 1 over the natural log of 2 times x dx. So dy dx is just 1 minus 1 over ln of 2 times x. And we want to know what is it when it's 8. So the differential of y with respect to x when x equals 8 is 1 minus 1 over natural log of 2 times 8. Right? And other than getting an estimate for this, this is the best we can do for our slope because natural log of 2 is not some rational number. So this is our slope. And then we put it into point slope form for our tangent line is going to be y minus our y coordinate, which we calculated as 5, is equal to our slope, 1 minus 1 over 8 ln of 2 times x minus our x coordinate, which is 8. And there is the equation of our tangent line. I know it looks kind of unattractive because our slope is this irrational number here, but without getting an estimate, that's as good as we can get. And it's exactly what I want.